Going to.
Alright, I hope this is working.
Lights
In full
on.
disclosure here, we already did this video once,
Yeah.
and it didn't work. We did the whole thing, and we found out it didn't record. So we're doing sound today. Welcome to sound. And try and be original.
Yeah.
I'm just praying that this little green light means that it actually is working. Alright? I do have, what class are you guys again?
2022.
The class 2022 classmates here. You guys go ahead and say hello.
Hi.
What's
All right.
Gucci?
Why?
Alright, so let's move forward. If you guys can keep yourselves in control. It is sound. We did this before. You guys had a test run. Give me your best Chewbacca. Is that gum?
Yes. Throw it out, Tristan.
Alright, so we're working on sound. Here we go. Excessive sound seem appropriate for the sound notes. It says that. Starting off with the brain pops. That's the first thing you have to do. So take a time out and go watch your brain pops. Welcome back. Alright, now just to prove that you are going to do these correctly, I want you at the very top of your page, before you write this down, don't write it yet, I want you to write fish underneath note topics at the top of your page.
Oh, I already wrote it.
Fish underneath note topics at the top of your page. I will look for this when I assess whether or not you've done your homework.
Fishy, fishy.
Alright, so let's talk about the basics. What you really need to know. Sound caused by vibrations, okay? In order for something to make a sound, it needs to vibrate first. I just said it again. Source of sound must vibrate. You probably don't need to look. If you want to just sit back, you can probably just listen to me and write these in. Okay. Our examples. Got a couple of simple examples. The drum, if you've done the sound station in our station activities, you've seen it vibrate. You've seen the little paper clips vibrate. Car speakers, if you can actually see them, you'll see that they vibrate as well. We might do a little experiment with that. Run a little bit behind this year, so we might not make it this year. And vocal cords. Most of us have done this in class where you touch your voice box and you do a low-pitched hum. And you can hear your vocal cords vibrate. All right. And this is our good old tuning fork. It's a nice example. You can actually see it vibrate, and you know that it causes a sound.
Make the cat jump.
All right. All right. Moving forward. All right. I don't know what this thing is. I'm going to leave it there. It looks like that dragon thing without the wings and not nearly as cool.
Are you talking about Toothless?
Okay. So let's talk about the basics of sound. Sound travels in what we call a mechanical wave. Mechanical waves means it needs to actually have these. That's your atoms or your molecules. One atom will bump into the other. Kind of works similar to the way heat moves when we talked about conduction, but in this case it's just a compression wave, and that results in sound. Alright? It's a form of kinetic energy because it's molecules in motion. Okay? And it must travel through something called a medium. A medium is just a fancy way of saying it's traveling through something. So either a gas, a liquid, a solid. We did a couple of little demos in class with the laser pointer and the glasses of water. Remember, the gas was a medium. The glass, even though it's a solid, was considered a medium. And the water was also considered a medium. Okay. The atoms will bump into each other, and this creates what we call a wave. Much different than a light wave, but it's still a wave nonetheless. This is a great, in my opinion, one of the best interactives that we have. I can't play it for you here, but I'll put a link to it if you guys want to do the little clap video. You can actually see the air molecules compress and move apart as they travel throughout a room. Alright, so the basics. Again, sound is caused by something vibrating. This vibration causes the air molecules next to it to press into each other. Alright. And this causes what we call a longitudinal wave. So sound waves, the sound wave's energy travels the same direction as the wave, and this is what we call a longitudinal wave. Alright? Everybody got longitudinal wave? Alright. Longitudinal waves have two main parts where the molecules are pressed together. This is called compression. We've all heard that word before. Compression is when things are pushed together. The new one for us is the word rarefaction. Can you guys say that?
Rarefaction.
Let me say it, then you say it. Rarefaction.
Rarefaction.
Good job. All right, rarefaction is where the molecules actually, after the wave passes, they kind of spread out a little bit, and they're spaced a little farther than they normally would be, and they kind of bounce back to just normal spacing. All right. Okay, moving forward. This is big. It's definitely on a test. Where will sound move the fastest, the slowest? Fastest is by far and away going to be in a solid. And that's because the molecules are close together. It takes a lot less time for this molecule to bump into this molecule if there's not as much empty space between them. All right. Which means the fastest in a solid, the slowest is probably going to be in a... You guys already noticed we did this twice.
Yep.
In a gas. Okay? That's where the matter is packed least. I don't have it in your notes, but where is it going to travel kind of a medium speed?
The
Liquid. Very good. Guess liquid, you did good. Okay. So, now we did the bell jar in class as well, and that's where we created a vacuum. Now, sound waves, because they're mechanical waves and need molecules, they can't travel through a vacuum because there are none of these. No molecules. That's where that great saying comes in movies.
You can't scream in space.
No one
Everybody-
can hear you if you scream in
You
space.
can't
Scream in space.
Yeah,
No
you-
one will hear you screaming.
Well, we got 4 different versions of this. My head hurts from doing this 4 times. But some version of you, nobody can hear you scream in
We
space.
said that. Yeah.
Well, you said a version of that.
I said
But
the
it's the
actual
same
thing.
thing.
Oh, I can't handle this.
No one
All
cares.
All right. Bell jar demonstration. If we were doing this in class, we would now do the bell jar demonstration. You guys got to be quiet while I'm talking, please. But since we're not doing it in class, you're doing it at home. Most of us have already seen the bell jar demonstration. If you haven't, some of you will see it today. By the time you're watching this, you should have all seen it. And that is the idea that a vacuum is created and sound waves cannot travel. All right, so let's get to our good old friend lightning. All right, what is lightning, by the way? Anybody remember what it's called? What is lightning
Oh.
actually? Raise your hand, man.
Bro, I was
Maybe
like,
you should be Savage McGee.
An electric discharge.
Electric discharge. That causes 2 things to happen. All right. You can see an electric discharge that we call lightning, and you can also hear the sound that it makes, which we call thunder. All right. Now, in this situation, we're comparing a sound wave to a light wave. Remember, they're very different. But a light wave travels much faster than a sound wave. This is why, a lot of boinging. This is why you can see lightning way before you hear thunder. Especially if you're farther away. The farther away, the quicker it goes.
Spells it right this time.
All right. Moving on. What are we doing next? Sound waves. All right, we're going to talk about location. Now, up to this point, we've talked about sound as far as communication goes and hearing things that vibrate. Now, some humans, as well as some other animals, have developed a way to use sound to kind of figure out where they are located in their environments. We call this echolocation. This is when sound waves are bounced off objects to determine location. Okay. Some great examples. We have bats that are able to fly in the dark. Wonder how does a bat do this? It obviously can't see the trees or the insects that it's hunting. It sends out a real high-pitched squeak that its large ears detect. That squeak bounces off of objects, comes back, and their brains are made so that they can visualize through sound the environment around them.
The world's most powerful
Some other
bird
big
blessings.
hitters, please stop. The other big hitters, whales. Whales are another big hitter. They're able to locate their food using this echolocation as well. Dolphins do this. You ever heard dolphin? You've gone to a like SeaWorld or one of those shows. Dolphins make that real high-pitched sound, and they use this in the same way. Now, as humans go, we have adapted this for fishing boats. If you've ever been in a boat, they can tell how deep the water is, or can tell where there are big schools of fish. It's because the fishing boat's sending off a little sound, and it's bouncing off the object, coming back to the boat. It's timing how long it goes, and it calculates the distance to those objects. And to be honest, we're not nearly as good at this as animals that have evolved to have it, like bats and whales and what are those other things we said?
Dolphins.
Dolphins. Thank you.
Pet dolphins.
So again, our examples are the bat. I got a dolphin, and of course, I didn't think about this before. Submarines. Submarines do this as well. That's how they're able to navigate under the water. And if you've ever seen a movie with a submarine, you can hear it go ping, making those pinging sounds. Now, it's at this point that we're going to have a little competition. I want to make sure you are watching the videos and not just skipping ahead. Let me see this for a second. On your paper, you have this little picture, okay? Right to the right of it, right here. I want everybody to draw your best picture of a fish. Ready,
Yes.
set, go. You have 10 seconds.
Wait, that's not fair.
And Billy wins the speed round with the goldfish. The snack that
Smiles back.
smiles back.
Fish.
Nate with some version of a sharkish fish. I'm doing yours last. All right,
Not done
come on.
yet.
Everyone-
Time's up.
Vote for
Fine,
Justin.
he's done.
There's
Everyone,
Megan's.
Oh
Looks
yeah,
pretty
you're
good.
using the other one.
Gotta
Vote for the
stop-
last
please-
one.
Please stop talking while I am. And I don't know if this is called an arrowfish or what we have here. This is the most disturbing animal.
vote for the last one.
I'm just going to say this. If I was snorkeling and I came across this fish,
You would say, "Oh, that's an attractive fish."
I would be terrified for my life.
We will be having a
Okay.
voting board.
Okay, moving forward. This isn't in your notes, but just so you understand how it works, our eardrums are basically a large membrane, well, large for the inside of your ear, that detects these slight changes in the spacing of the molecules, which is then, through a couple of other bones, transformed eventually into a electrical signal in your brain, which we interpret as sound. And that's kind of how it works on our end as far as hearing sound. All right, Justin. So, that's good with the headbanging. Here's kind of the basic look of the internal structure of an eardrum and how it eventually is turned to a electrical impulse in your brain. We have one more brain pops I do want you to do on hearing. It's going to expand upon this a little bit because I think it's important you understand how you go about hearing things. Take a minute right now. Go do your brain pops. And I think we're going to call that good. Second time's a charm. I hope this recorded.
Yeah.
What class are you guys again?
2020.
2020.
No, not 2020. 2022.
2022?
Yeah.
All right, you guys can all say goodbye. Goodbye.
Bye.
Adios, amigos.
All right, and there it is.
Special goodbye from Goodbye, Savage McGee. everybody.